This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Chapter 1 of Black Holes Explained, where we're diving into one of the universe's most dramatic transformations: how a brilliant shining star can collapse into something so dense that not even light can escape. Today we'll walk through the incredible journey of massive stars from birth to their explosive final moments, and discover exactly what it takes to create these cosmic monsters. Let's get into it. A single dying star can briefly shine brighter than every other star in its galaxy. In this episode, we drop into the final heartbeat of such a giant, when light, matter, and even time itself face a question with no escape. What happens after the last burst of fusion? In that final instant after a massive star's core gives way, the universe runs a kind of high-stakes audit. Every particle, every bit of energy, every fragment of the star's history has to decide where it goes: flung outward into space, locked into an ultra-dense remnant, or lost behind an event horizon. The result isn't predetermined. It depends delicately on the star's mass, rotation, and internal structure at the moment of collapse. Some stars leave behind neutron stars, atomic nuclei scaled up to city size, while the most extreme cases cross the line into black holes. Astronomers read the outcome not by watching the core itself, but by decoding fleeting signals: a flash of gamma rays, a fading supernova afterglow, a storm of escaping neutrinos, and long afterward, ripples in spacetime from black hole mergers. Astronomers rarely witness this drama in real time. Instead, they reconstruct it from remnants scattered across millions of years. Supernova shockwaves compress nearby gas, seeding future generations of stars and planets, while the densest leftovers orbit quietly in binary systems, betraying themselves only through X-ray outbursts or gravitational waves. In this episode, we'll zoom out from the collapsing core to its wider ecosystem, how a single death event reshapes its stellar neighborhood, and how black holes emerging from these ruins connect to the mergers LIGO detects today. Far from the collapsing core, the star's outer layers are still following orders from a past that no longer exists. For a brief moment, gravity is pulling them inward toward a core that has already transformed, while an outbound shockwave races upward to unbind the star. Whether that shock actually succeeds is the first big fork in the road between a visible supernova and a quiet, almost invisible birth of a black hole. If the shock stalls, the star can undergo fallback. Some of the material that started to escape loses momentum and rains back down. That returning mass can push a borderline neutron star over the Tolman, Oppenheimer, Volkoff limit, turning a near miss into a black hole seconds or minutes after the initial collapse. Astronomers suspect that some dim, failed supernovae, where a massive, bright star simply winks out over a few months, are signatures of this gentle-looking but lethal outcome. Rotation and magnetic fields add more branches to the story. A rapidly spinning core can flatten into a disk, feeding the newborn black hole. Under the right conditions, that disk focuses a pair of ultra-relativistic jets that punch through the star and power long gamma-ray bursts. These events are so luminous that we can detect them from billions of light-years away, yet the central engine can shut off in less than a minute. Most massive stars don't live or die alone. In close binaries, one star may already have become a compact object when its partner collapses. Mass transfer before the explosion can strip off the outer envelope, altering how much material is left to form the remnant. Afterward, the kick from the explosion can either disrupt the system entirely or tighten it into a doomed black hole pair. Over millions to billions of years, gravitational radiation robs such binaries of orbital energy until they finally merge, producing the space-time ripples that LIGO detects. Across a galaxy, thousands of these individual fates add up. Each death event enriches interstellar gas with heavy elements, shapes new star-forming regions, and quietly seeds the population of stellar mass black holes that future observatories will map in detail. Your challenge this week? Treat every news item or image about a massive star or supernova as a branching decision tree. Ask, did the shock win or stall? Was there fallback? And could this be the origin story of a future black hole merger? In hospitals, a patient's chart can branch into ICU recovery, long-term rehab, or a final, flatline, depending on a few key vitals. Massive stars have similar care pathways, but their metrics are mass, spin, and chemical makeup. A star born with just a bit more mass than its neighbor might end in quiet collapse with almost no fireworks, while the lighter sibling erupts in a vivid, widely photographed supernova. Metal-rich stars, those formed from already processed gas, tend to shed more of their outer layers through stellar winds, trimming down the mass that can feed a future black hole. Metal-poor stars, especially in the early universe, may keep their bulk and collapse more directly. In dense star clusters, close encounters can swap partners in binary systems, pairing black holes that never formed together. Each tweak, a faster spin here, a stripped envelope there, rearranges the routes that lead from solitary giants to the merging black holes we detect billions of years later. Soon, black hole births may feel less like rare fireworks and more like a constant, low drumbeat in our data. Collapses across cosmic time will sketch a kind of population census of gravity's most extreme offsprings. Patterns in their spins and masses could expose how often stars share partners, trade mass, or die alone. Like tracing family traits through generations, we'll follow how each collapse subtly reshapes galaxies, star by star, until the sky looks more like a living family tree than a static map. Across billions of years, these endings quietly rewrite the universe's playlist, adding heavier elements that later become planets, oceans, machines, and us. The next black hole birth you read about isn't just distant fireworks. It's an upstream note in the chain of events that eventually makes technology and curiosity about this story possible. Here's your challenge this week. One evening after dark, go outside and use a stargazing app like Stellarium or SkyGuide to locate at least one star that's more massive than the Sun, for example, Betelgeuse or Rigel in Orion. Then look up its estimated mass and fate, neutron star or black hole candidate. Sketch a simple life timeline for that exact star. Birth in a nebula, main sequence, red supergiant, supernova, then black hole, or not, with rough timescales in years. Finally, explain its whole death journey aloud, in your own words, as if you're narrating the star's path to becoming a black hole for a curious friend standing next to you. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!